This should be the last video for chapter 14. I'm going to start with the focus of conditional probability and independence. So let's just give ourselves a little bit of a situation here, right? So let's suppose we're going to toss a coin twice, okay? We'll define events A as being the first toss being a heads, okay? And we'll define event B being that the second toss is going to be a head. So then I would know that the probability of A would be 1/2, and I know that obviously the probability of B would also be 1/2. Okay. So then what if I asked you for the probability of B given that A actually already happened, right? So in other words, I flipped a head on the first toss. What's the likeliness then of flipping a head for the second time, right? Well, we know that the one wouldn't affect the other. The coin has no memory. It doesn't know that it tossed the coin a head the first time. So the probability that this would happen would still be 1/2, because what happened the first time is not going to affect what happens the second time. Okay. Things like this, though, aren't always true. So let's kind of contrast that scenario with that pierced ears situation, right? So students with pierced ears that we saw in the first two videos. So the chance process involved randomly selecting the student from a college statistics class. The events of interest were A, that they were male, a male student, or B, that they had pierced ears. Okay. So I knew that the probability of A was 90, because there was 90 males out of a total of 178 students. But the probability of B was 103, because there was 103 total with pierced ears out of the 178 total students. But when we found the probability of B, given that given that we know it fits the condition of A. So in other words, what's the probability that they have pierced ears, given that we know that they are a male student? Well, now we know that they are male students, and of those male students, 19 had pierced ears. Okay. So if we know that the chosen student is male, the probability is 19 over 90. This conditional probability is very, very different from the unconditional probability of 103 over 178, the probability that they would have pierced ears. Okay, so when knowledge, so hang on, let me get back to my PowerPoint so we can see that. So what I'm demonstrating here is the idea that sometimes events are independent and sometimes they are not. So when knowledge that one event has happened does not change the likelihood that another event will happen, we said that the two events are independent. So two events, A and B, are independent if the occurrence of one event has no effect on the chance that the other event will happen. In other words, events A and B are independent if the probability of A, given that B happens, is equal to the probability of A, and the probability of B, given that A happens, is also just the probability of B, meaning that it doesn't matter what happened already, that next event isn't going to change, okay? So here's kind of a quick example to demonstrate that. So is there a relationship between gender and handedness? To find out, we use Census at School's random data selector to choose an SRS of 100 Australian high school students who completed a survey. The two-way table displays data on the gender and dominant hand of each student. Okay. So the question is, are the events male and left-handed independent? And let's justify our answer. Okay, so the probability that they are left-handed given that they are male. Okay, so we're looking at only that row there, so that they are given that they are male. So always concentrate on what that second thing is, okay? There's 23 males, 3 of them are left-handed, okay? So then we're going to want to see, is it the same thing if I asked you if they were just left-handed? Because if they were independent, then these would be the same. Okay, meaning it wouldn't matter if that they were male, you'd still get the same answer for left-handed. So let's go to our left-handed, and we have 7 out of 50, which totals 0.14, which is different. So because the probability of left-handed, given that they are male, is not the same as the probability that they are left-handed, means that these are not independent events. Okay. So when events A and B are independent, we can simplify the general multiplication rule a bit. Okay, so the multiplication rule for independent events looks more like just multiplying the two together. So you don't have to worry about the condition. Okay, so here would be a example of that. So following the space shuttle, okay, so backing up a little bit. So on January 28, 1986, Space Shuttle Challenger exploded on takeoff. All 7 crew members were killed. Following the disaster, scientists and statisticians helped analyze what went wrong. They determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Under the cold conditions that day, experts estimated that the probability that an individual O-ring joint would function properly was 0.977. But there were 6 of these O-ring joints, and all 6 had to function properly for the shuttle to launch safely. Assuming that O-ring joints succeed or fail independently, let's find the probability that the shuttle would launch safely under similar conditions. So because if one O-ring fails, it's not going to determine whether the next or any other of the O-rings would fail, we would consider this to be independent, which means we don't have to necessarily worry about what's the probability of O-ring number 2 failing if, or functioning properly if O-ring number 3 did not, okay? So you don't really care about what happened to the others. They're completely independent of each other. So what we see above here is that we can just multiply all of these out, okay? So the probability of joint 1 is okay or functioning properly, and 2 is functioning properly, and 3, and 4, and 5, and 6. So I'm going to do the probability of joint 1 times 2 times 3 all the way to 6. So in other words, 0.977 times 0.977 6 times. In other words, 0.977 to the 6th power, which is 0.86. So in other words, there is an 87% chance that the shuttle would launch safely under similar conditions, and about a 13% chance that it didn't. Okay, so now to talk about, I think, one of the last things. Okay, so the next example uses the fact that at least one and none are complete opposites. So when you see the idea of at least one, you could just think of it being the opposite of none. So the probability that at least one outcome happens is 1 minus the probability that no outcome happens. So here is a example that demonstrates that, and then we will be done. Okay, so many people who come to clinics to be tested for HIV, the virus that causes AIDS, don't come back to learn the test results. Clinics now use rapid HIV tests that give a result while the client waits. In a clinic in Malawi, for example,
Use of rapid tests increased the percent of clients who learned their test results from 69% to 99.7%. The trade-off for fast results is that the rapid tests are far less accurate than the slower lab tests. Applied to people who have no HIV antibodies, one rapid test has a probability of about 0.004 of producing a false positive. That is of falsely indicating the antibodies are present. If a clinic tests 200 randomly selected people who are free of HIV antibodies, what is the chance that at least one false positive will occur? Okay. So, I could do it here. Okay. So, test results for different individuals are obviously going to be independent. What one individual tests doesn't affect if the other one will have this whatever effect for the other, right? So we know we have 200 independent events here. The people here are definitely independent, okay? So each of these has a probability of 0.04 that there's a false positive, okay? Is it a false positive or a false negative? A false positive, okay? 0.004 that they have false positive, okay? So this idea of at least, okay? So what is the probability that at least one false positive will occur in these 200, okay? So this is going to combine many possibilities, right? So this is like saying the probability of at least one positive would be 1 minus the probability that there are no negatives, right? Because we talked about the idea that it's the opposite of none. So if it's the probability of at least one positive, it's going to be 1 minus the probability of no negatives. Okay. So the probability that there are no positives is equivalent to the idea that all 200 be negative. So in other words, that's the 0.996 times 0.996 times 0.996 200 times, so to the 200th power, which is going to give me 0.4486. Okay? So then the idea that we have at least one positive or one false positive, that is, would be 1 minus all 200 being negative. So 1 minus 0.4486. Right? So about 55%, we can say. So there is more than 50% chance that at least one of the 200 people will test positive for HIV, even though they don't actually have the virus. And that is it.